information for the semester. We'll work on this today and tomorrow, and then on Monday and Tuesday next week we'll be reviewing for our chapter test, and our chapter 7 test will be on Wednesday. The notes start off talking about the word continuity. So in math, we describe graphs as continuous or discontinuous. And you can probably just think about those words and figure out what they mean. In math, we, up until this point, have really probably spent 99% of our time graphing continuous graphs. Meaning, if I plot a few points for a line, then I can take my pencil and draw the whole line. If I plot a few points for a quadratic function, then I can take my pencil and with one smooth curve, never picking up my pencil, I can draw a parabola. The graph that happens in chapter 7, the rational function graph, is not a continuous graph, meaning I cannot draw all parts of the graph without having to pick up my pencil. So what we see in this chapter is something that is discontinuous. And that's a result of the fact that the function is a fraction. And we have some issues with fractions. Okay? So there are two types of discontinuity. One of them is a point. You can have a point of discontinuity, and that is called a hole. This is one of those topics where we're going to talk about it today in the notes, but we're actually not going to see an example with a hole until tomorrow. So a hole is any point or any x value, and then its corresponding y value, in which the numerator and the denominator share a common factor. So we know what that looks like from multiplying and dividing and simplifying fractions. If we factor the numerator and we factor the denominator and we say, oh hey, they both have x plus 3, I could cancel those out. What that means in the graph is at x equals negative 3, there will be a place, and it's just we'll draw it like an open circle. There'll just be one single point where I'll have to draw an open circle, and I'll have to pick up my pencil and go to the other side. And so at that particular point, there is no answer. So it'll just have a hole. The other type of discontinuity that we can see is created by asymptotes. Okay. Now, you have seen asymptotes already. We talked about asymptotes with exponential graphs, and I thought we talked about asymptotes with something else, but I'm not for certain. Perhaps not. But the asymptote is this line that your graph gets really, really close to but never actually touches. Horizontal asymptotes do not create points of discontinuity. You can just go, you can still get that nice curve, keep going left, keep going right, and everything is cool. But in rational functions, we're going to have something called a vertical asymptote, one that goes up and down, and it basically cuts our graph in half and says some stuff goes on the left of this line, some stuff goes on the right of this line, there's nothing on this vertical line. So that's going to be another place where we have discontinuity. We're going to have to pick up our pencil and move to the other side of the asymptote. So that one will look a little bit different than a hole because it won't be like your graph is coming in to the hole. It'll just be this line that on either side we get really, really close to but never actually touch. Okay. Now, rational functions generally have the shape of a hyperbola, so it sounds kind of like parabola. The big difference between a hyperbola and a parabola is a hyperbola is actually two U-shaped curves instead of just one. And those U-shaped curves are called branches. So I put in two pictures of what a hyperbola might look like, and if you want to, you could label in this picture, I have a branch in the first quadrant, and I have a branch in the third quadrant. Some of you might be able to fill in by looking at the graph that you do have some asymptotes. You have some lines that your graph is getting really, really close to, but never touching. For example, the x-axis. On the right side, my graph is coming really, really close to the x-axis, but it's never going to get there. On the left side, we're getting really, really close, but we're never going to be there. So we have an asymptote, a horizontal asymptote. We also have in this graph a vertical asymptote. So what's nice about this is the horizontal and the vertical asymptotes become the boundaries for the branches of the hyperbola. So you'll always have two branches for the graphs that we do. It's not true for all rational functions, but for the ones that we do, we'll have two branches. And they'll always be sort of trapped by those two asymptotes. Okay? And the other thing about the branches is they always are like opposite of each other. I call it catty corner. Some people might call it like kitty corner. But like if one's in this like top right, then the other one's in the bottom left. You could have branches in the bottom right and the top left, okay? But they'll never be in the little areas right next to each other. They'll always be opposite of each other. Okay, so what we are going to do is we are going to let P of x and Q of x be polynomials. Okay, think about your polynomials unit. They look lots of different ways. They can look like constant terms. They could look like linear functions, quadratic functions. We probably won't go much higher than that. But they are some polynomials. And f of x is going to be our rational function. Remember, rational function has the word ratio, so it looks like a fraction. And our fraction is p of x over q of x. So we have some polynomial p of x in our numerator, and we have another polynomial q of x in the denominator. These graphs have the following characteristics. The x-intercepts are the real zeros of the function I'm going to come back to that one a little bit later, and we're going to add some thoughts to that. The graph of f of x has a vertical asymptote at each real zero of the denominator. And there is a hole in the graph for every factor shared by the numerator and the denominator. I'll go to the next slide to talk about horizontal asymptotes here in just a second, but note that a rational function can have only one horizontal asymptote. So it says at most one horizontal asymptote. That is not true for vertical asymptotes. It is possible for rational functions to have more than one vertical asymptote. It just breaks up our graph into different sections, okay, left and right. Okay. But one horizontal asymptote is the max that you can have. The other thing that you might do is when I talk about the denominator, look back at this math notation that we use where f of x is equal to p of x over q of x. When I say that the vertical asymptote is at each real zero of the denominator, I'm talking really about q of x. And when I say the real zeros of q of x, that would mean I take q of x, whatever that polynomial is, and I set it equal to 0. And if I set it equal to 0, I could solve for x, and those will be the real zeros. Okay. When I talk about the numerator and the denominator, I'm saying, do p of x and q of x share any common factors? So you'll be factoring the numerator and factoring the denominator and checking to see if they have any common factors that will disappear. Okay. This one, where we're talking about the x-intercepts of the function, then we're really talking about f of x as a whole. When is f of x equal to 0? And I'm going to come back and talk about that one again, because there's a shortcut later on. Okay. Now let's get down to the horizontal asymptote piece. Okay. The horizontal asymptote is determined by the degree of p of x and q of x. So we need a little refresher from chapter 4 in semester 1. When I talk about the degree of a polynomial, what am I referring to? What is the degree of that polynomial? Is it the coefficient of x squared? Thoughts?
Oh, I remember this. No.
Do you agree with Eric? Yes? Do we all agree with Eric?
Oh, no.
Oh no. Skylar's changing her mind.
Wait, what did Eric say?
What did you say?
Would it just be one?
I just heard what you said.
What's in front of x squared?
Oh, he's saying 1 because it's what's in front of x squared.
I think it's the highest exponent.
So you think it's what number?
2.
2 because it's the highest exponent. Eric, what do you think? Still 1?
Yeah, I think
Oh, then he remembered that it is 2. It is the highest exponent. So let's write this down. The degree is the highest exponent. Thank you, Skylar, for remembering.
2.
Okay, the degree is the highest exponent. So we would say here our degree is 2. What is that number that Eric called? Because we're going to use it later. He called 1, the number in front of x squared. What's that named? What are numbers that get multiplied in front of variables called? Coefficients. And this one is the leading coefficient, because it's the one that should be at the front of standard form. Okay, very good, Riley. So let's label that one. We'll need it later. Okay, so that's going to be our leading coefficient. Okay, so what we're doing is we are comparing the highest exponent in the numerator to the highest exponent in the denominator, and that's going to help us determine our horizontal asymptotes. Okay, so if the numerator's degree is less than the degree of the denominator, then the line y equals 0 is your horizontal asymptote. So this is like numerator degree and denominator degree. Okay, so we're talking about the highest exponents. If the numerator's degree equals the degree of the denominator, then dividing the leading coefficients determines the horizontal asymptote. So knowing that number is important to us. Then dividing the leading coefficients determines the horizontal asymptote. And we'll actually work with that scenario tomorrow. Okay. And the last one, if the numerator's degree is greater than the degree of the denominator, then the graph has no horizontal asymptotes. If you take Algebra 3 next year, you'll find out that instead of a horizontal asymptote, it has something called a slant asymptote, because it's a line that has slope other than 0. Now, at the very bottom of this page is a very important statement. So if you have a highlighter, I suggest you highlight this. If you have a different color pen, maybe circle, underline, box it in pen. You could bubble it. This is very important. If there happens to be a constant that gets added or subtracted to the function, so like you have p of x over q of x, a polynomial divided by another polynomial. If behind that fraction you put a plus or minus something, that's a vertical shift. That's like going up and down k units like we used to do. So that moves your whole graph, including your horizontal asymptote. Okay. So if I were to have the numerator's degree less than the degree of the denominator, I would normally say the line y equals 0. But if I have a k value in the back, then my whole graph will get shifted up or down k units, and that 0, y equals 0 asymptote will do the same thing. So if you see a k, something that's added or subtracted behind, then that's going to be affecting your horizontal asymptote. And most likely for the very first case when the numerator's degree is less than the denominator's degree. So we're going to see that today. Okay. Okay, so after talking about k, I just want to go back real quick to that previous slide, and it's just a little bit up on yours, and talk about the x-intercepts. The x-intercepts will be the real zeros of the function. If there is no k, you can set your numerator equal to 0. And that will help you find your x-intercepts. If k doesn't exist, you don't really have to worry about your denominator at all. Okay, so you can just ignore it and set it equal to 0. If k exists, I'll show you in our second example what to do if you have a k value so that you can find your x-intercepts. It's a little bit less nice than just setting your numerator equal to 0. You have a little bit more algebra to do. Okay, but that will help you find the zeros of the function. Hello. Can you work in here? Yeah. Okay, on the back you have an example, f of x equals 2 over x plus 3. And we want to find x-intercepts, vertical asymptote, horizontal asymptote, domain, range, holes, anything that it might have. Let's start with x-intercepts. Go back to the front side. What do you know about the x-intercepts? They are what? The real zeros of the function. And we also wrote down, if there is no k, what can we do? Set your numerator equal to 0. Do we have a k here? No, there's nothing added or subtracted behind that fraction. So if there is no k, I can really just set my numerator, which is 2, equal to 0, and try to solve it. How do you feel about the equation 2 equals 0? Are you cool with that? No, 2 is not equal to 0, right? I would rather have $2 than $0. So 2 is not equal to 0. That means there is no real zeros to the numerator or to the function, and therefore there is no x-intercept. Just keep your phone away. Vertical asymptote. What do we have to do to find the vertical asymptote? Flip over your sheet. Find. What does it say for vertical asymptote? It says there.
Find the real zero.
Denominator. Find the real zeros of the denominator. So that means set x plus 3 equal to 0. Can you solve x plus 3 equals 0? Yeah, what do you have to do to both sides? Subtract 3, so you get x equals negative 3. So that means I have a vertical asymptote at x equals negative 3. I'm going to go ahead and draw that on my graph. X equals negative 3 is left 3, and that's a vertical asymptote, so I'm drawing a line that goes up and down. There's my vertical asymptote. Horizontal asymptote. That's the last thing we talked about before our examples. What do we have to look at to decide horizontal asymptotes? Look at the degrees, right? This is where we had the discussion about degrees, highest exponents. So we're going to look. What is the highest exponent in this numerator? Do you see x to the first? No. If you don't even see an x, what must its exponent have been? 0, because x to the 0 is equal to what value? Anything to the 0 is equal to 1, so it totally disappeared. We don't even see it. So the degree of the numerator is 0. What's the degree of the denominator? X to the first. Now we can say 1 because we see an x. So here we have the degree of the numerator, I'm just going to abbreviate n, is less than the degree of the denominator. If you go back to the front side, that tells you your horizontal asymptote should be at y equals 0. Y equals 0 or y equals k, but we don't have a k, right? So y equals 0. Okay. Excellent. Write that down and mark that on your graph. Y equals 0. That's your x-axis. You're not going up or down anything. Yeah. What's really nice about this is we now have two asymptotes. We would like to know where the branches of the hyperbola belong. Okay. And in order to do that, we can pick some x and y values. I'll tell you, I think you really only need, for my purposes, one x and y. Because if you know one point, you know where the other point is. Perfect. Now, you could choose any x that you want. The only x you cannot choose is the one that doesn't work, which is your vertical asymptote. If you put negative 3 in, you'll get something that's undefined, and that's not an answer. I choose x's that make my denominator equal 0. So what would I, or not 0, 1. What would I have to put into my x to make my denominator equal 1? Negative 2? So I'm going to put negative 2 in for x. And I know that that's going to make my denominator equal 1. So then I'll just have 2 over 1, which is 2. So that makes it really easy. If you can find the x value that makes your denominator equal 1, that makes it really easy to evaluate. And now you plot the point negative 2, 2. So I'll go left 2, up 2. I think you only need 1 point because now I know where one branch is. One branch is in like that top right section created by my asymptotes. It's going to approach the asymptote here. It's going to approach the asymptote there. Right? That's what it does. It gets trapped by those two lines that are marked as asymptotes. And do you know where the other branch should be? Based on the pictures on the front side? Yeah, in the like bottom left of those two asymptotes. They have to be catty corner from each other. Could you find another point if you wanted to and get an exact point? Absolutely. That would not bother me at all. I just don't think that you need to. We're not going to use the graphs for anything else. So you really just need to know like where your graph is going to show up. Okay. Okay, now we still have a couple things to discuss, domain and range. Okay. What's really nice about the rational functions is the asymptotes tell you what domain and range will be, or what domain and range can't be. So domain is everything that you can put in for x. I can put in everything for x except what number? Negative 3. That's my vertical asymptote. So my domain is all x's not equal to negative 3. That means, in short terms, anything except 3. Or negative 3, sorry. So my horizontal asymptote is everything I can be for y's. And I can be anything for y except 0. I never get to 0 because that's a horizontal asymptote. So I'll say y is not equal to 0. Now, it says list holes. Holes are created by common factors in the numerator and the denominator. Do our numerator and denominator share any common factors? Not today, right? There's not a factor of x plus 3 in the top and the bottom that I could cancel. Okay, so if you don't have any shared factors in the numerator and denominator, then you have no holes. You can write none. You could put NA for not applicable. Just say there aren't any holes. Okay. Questions about what I did right there? I'm going to do one more example, and then I'm going to have you do the third one at your tables. Okay. So the next one is f of x equals 5 over x minus 8 minus 3. Okay. Notice what's different about this one than our first one? It has a k value, right? Okay. So this k is going to complicate my x-intercept. I can't simply say there are no x-intercepts because 5 does not equal 0. So I'm actually going to do my work for my x-intercepts. I'm going to pull that down right here. If you go back to the front side of your notes, it says the x-intercepts are the real zeros of the function f of x. So that means make f of x 0. Okay. So I'm going to say f of x is 0. 0 equals 5 over x minus 8 minus 3. And now I'm going to work to get x all by itself. Well, the first thing I have to do is add k to both sides. So add 3. That gets me 3 equals 5 over x minus 8. If I have 3 equals 5 over x minus 8, how could I solve that? Multiply by x minus 8? Sure. What you're really doing there, is the real version of cross multiplication. Okay, you're multiplying that by both sides. And then we get something like, we'll have to distribute 3x minus 24 equals 5. And now I could solve. Add 24. So 3x equals 29. Divide by 3. And I know that 30 divided by 3 would be 10. This is only 29 divided by 3, so I'm probably like 9.7, 9.6. That would be 9 2/3. So 9.6 repeating, so I'll say 9.7. So I have an x-intercept at 9.70. No, yes, I did do that. Yes, that's right. Meaning go right 9.7, go 0 up or down, so you're on the x-axis. Okay, so that one's a little bit more trouble, finding your x-intercept. Okay. Now, the other one should go a little bit quicker. Vertical asymptote. How do we find vertical asymptote? Set x minus 8 or the denominator equal to 0. Awesome. X minus 8 equals 0, so x equals 8. Okay, good. Go ahead and mark that. 2, 4, 6, 8. To determine my horizontal asymptote, I'm going to check the degrees of my numerator and denominator. I'm going to find the same thing out that I had last time, right? The numerator's degree is 0, the denominator's degree is 1, so the degree of the numerator is less than the degree of the denominator. My horizontal asymptote should be at y equals 0, unless you have a k, then it will be at y equals -3. So I'll go ahead and mark that, y equals -3. Now I'd like to know where my two branches show up, so I'm going to do an x and a y. Remember, I always strategically choose my x so that it makes my denominator equal 1. What would I have to put in for x so that x minus 8 was equal to 1? 7 minus 8? 9 minus 8. Either one would be fine still. The 7 will just make it negative. But I'll keep it positive, so I'll do 9 minus 8 is 1. 5 over 1 is 5, and then 5 minus 3 is 2. So you have a point at 9, 2. Makes it really easy to evaluate if your denominator is equal to 1. Plot that 9, 2, so I'm going 9 to the right and 2 up. I could also plot my x-intercept at 9.70. And then I just have to draw my graph. It's going to be trapped inside those asymptotes. I shouldn't have crossed my asymptote by marker, just on the smartboard. It's a little hard. It shouldn't be that close. And then I'll draw one down here. I have a graph. By having one point in any section on your graph, you know immediately where your two branches will be, because they have to be opposite of each other. And then domain and range, after you have vertical and horizontal asymptote, those are really easy. Domain always goes with x, so just say x cannot be 8. Range always goes with y, so y cannot be -3. But we don't have any common factors in the numerator and denominator yet, so we don't have any holes. We will have holes tomorrow. We've got about 6 minutes. I would like for you to get started on example 3. Okay, so work through example 3 at your tables. Talk to each other. If you need help, flip that paper over. Read what you need to know about horizontal asymptotes, vertical asymptotes, etc. Okay, see what you can get done. Okay, for that third example. That's technically what? Okay, you're looking at degrees, not numbers. So the degrees are the things on x's. So like, can I borrow your pen right here? This is x to the first, and this doesn't have an x, so it was x to the 0. So you're looking at 0 and 1, but not any of those other things. Does that make sense? If there is no x in the numerator and there's any kind of x in the denominator, it's going to be smaller because it has 0.
Just like well, this one's minus already.
So the numerator's degree is less than the denominator's, do you agree? Okay, so normally it would be, in that case, y equals 0, but you have a k. So it goes up 1, so it would be y equals 1.
So it'd be positive 1.
I think, is the x-intercept like negative 12?
Yeah.
Negative 12, 0, it's not?
I got
I think if you have 12, there's a small sign error.
I got negative.
Did you get negative 12? It should be negative because, like, when you graph it, you have a vertical asymptote at 4, you have a horizontal asymptote at 1, and like for my point xy, I choose 5, and then I'm going to get negative 7. Oh, it should be 12. It should be positive 12, sorry. It should be positive 12, because then your asymptote is like up here off the graph, right? So you can kind of check to see if you're right, if it makes sense with your branch. Okay, and then your other branch would be somewhere up here. You have an assignment, it's a worksheet, so make sure you get this before you leave. On the front are 4 graphing problems, just like the ones in the examples. On the back are some review problems, which will be helpful as we prepare for our chapter test. Bring this with you tomorrow. We'll go over questions and then we'll do extra examples.